happens, and we'll be fine. Okay. We now know the fundamental theorem of calculus, which has two parts to it, okay? If the function's continuous, then if I take the integral of that function, I get the antiderivative, right? Okay. Also, the way you can check this is if you take the derivative of it, you should get that back. Right? Okay. So if f is continuous, the integral of that thing is an antiderivative. And if you take the derivative of that, you should get this thing back. So you can check back and forth. Remember that on quizzes and tests, APs. You can check back and forth. The second part of the fundamental theorem of calculus says this. If I want to know, kind of right now, the area under the curve, I can do the integral from, where do I want to know the area of the curve from? From lower bound, upper bound of the function in terms of x, or function of t in terms of t, or remember that part. It can be found by evaluating, find any antiderivative of this, and plug in the upper bound minus plugging in the lower bound. Those are the two parts of the fundamental theorem of calculus. It must be continuous. That was the answer to one of the last question. You know, what's wrong with this logic? Oh, it wasn't continuous. Okay, so it's got to be continuous. And then the next, so you got to check that it's continuous, and then the fun part is in number 2, which means, why is it the fun part? Because you don't have to do rectangles and trapezoids and Simpson's rule and all that stuff. Okay? That's why we like it. So this integral notation is usually used for an antiderivative of f. That means we want to kind of go back. Antiderivative. And it's called the indefinite integral. Indefinite because I don't have a lower bound, upper bound. Okay? So this integral is the way we will write any derivatives. We'll kind of move away from this and just do this. Right? So again, if you take the derivative of this thing, you get that back. If you take the derivative of this thing, you get that back. Or if you take the integral of this, you get the antiderivative. We can move forwards and backwards. Here's the thing you have to remember most about today. A definite integral with a lower bound, upper bound gives you a numerical value. It's like the square root of 9. It'll give you something. An indefinite integral is not a numerical value. It is a function. We cannot plug in anything into it and get a definite answer. So a definite integral is a number. An indefinite integral is a function. Or more specifically, a family of functions, because the indefinite integral, we have to say plus c. So that means it can move up and down and be a collection or a family of functions. Just remember, this is a number. If you don't have it, the lower bound, upper bound, you're going to end up with a function. Otherwise, you're going to get a numerical value. Okay, what I handed out to you is some things I showed you in 6-1, way back when we were doing antiderivatives. And I would strongly suggest you can take the last 2 off. Integral of sine h and integral of cosine h. Take those 2 off. But I would strongly suggest that you put these on your yellow sheet in the next few days. So if you're somewhere and you don't have anything to do, transfer these to your yellow sheet. A lot of them you know, some of them you may have forgotten. But what's cool about all of these is not only can I read them from left to right, I can also read them from right to left. Because the derivative of this is that. The derivative of this is that. derivative of this is that. So the integral of that is this. Does that make sense? So you can read them forwards and backwards. So I would almost argue to you, you probably already have these on your yellow sheet from about 3 months ago. You probably added them going this way. But it's a good idea to put these on your yellow sheet to read them that way.
Y'all be good.
And again, don't worry about the last two, okay? Especially remember, you probably want to get these down for sure, because those were kind of weird ones when we did derivatives. Okay, don't worry about these last two. Is that cool? Let's do some examples. Find the indefinite integral of 10x to the 4th power minus 2 secant squared x in terms of x. I need that dx on there. Where we're going to combine what you have on that sheet with some of the properties of integrals generally, which means that I can do this. Let's see, some of the properties of integrals we did like a week ago, I think. Hey, a constant I can pull out front. And then I can just do this. Because these are separate terms. So I can break up the separate terms. I can also bring that 2 out here and do this. Whoops, if I spell it right. S-E-C, secant, square root of x, dx. Don't forget to put the dx. If I'm saying it equals this, then you better have all the parts. Or they're going to say, hey, you lose a point because it doesn't equal that. You want to have all the parts there. Okay, yes?
Do you factor the dx out, or do you always have to write it like that?
Always have to write it like that. Yeah, the dx has to be part of this. It's like doing something like that. If I just had that there, what am I going to do? Okay, or it's like doing this. If I don't have this here, what am I going to do? So yes, this is part of this. They go together. That symbol and that. Because it sort of represents change of x. Okay, so there's two properties of integrals here. I can pull constants out and I can break up pieces. Okay, so here I've got 10 that I pulled out. Remember how to do the power rule, the integral for the power rule? Going backwards?
Add 1 and divide by that.
Yeah, add 1 and divide by that. And once I've taken the integral, that and that disappear. I've done this in terms of x. Okay, the next one's going to be 2. And then, what is the antiderivative of secant squared?
It's 10x plus c.
Yeah, tangent x. And then actually this has a plus c, and this has a plus c all the way to the end, and a constant plus a constant is still going to be plus a constant. And we'll clean it up if we have to. I got 2x to the 5th minus 2 tangent x plus c. Notice that's a function. I did not get a numerical value. So if I did not get a numerical value, I gotta have that plus c. Be okay with that? Nothing scary, right? We're just using our properties of integrals and our integral formulas. Our antiderivative formulas, maybe. You want to think of it that way. Okay, what about the next one? What would I do here?
Can you do like the u, derivative u, v, derivative v?
Not until after tomorrow. That U substitution, well, actually, yeah, U and V is gonna be down, but, yeah, you could do that.
You can probably try to separate like that function.
Say that again?
You can probably try to separate like
Yeah, let's
change
see
the
if,
function.
yeah, let's see if I can play with it a little bit. I would try this, I would maybe break up the bottom. And then I've got cosine, sine over here. Right. Does that get me anywhere? Sometimes you gotta play with this stuff. A lot more so with integrals than you do derivatives. If I break that up, let's see what I've got. Well, what I've got is the antiderivative formula. See, that becomes this. 1 over sine is just cosecant,
Cosine over sine.
is cotangent. Is that the derivative of something? Does that have an antiderivative? Cosecant, cotangent?
Yes.
I think it does.
Negative cosecant.
Yes, this has negative cosecant. What's wrong with my lettering today? Negative cosecant x. Okay, I just took the antiderivative, that can go away. But I don't have a lower bound, upper bound, so plus c. Sometimes you gotta play with it. The good thing is, when you get to a deficit, all you need is an antiderivative. You need one that works. So sometimes manipulating it in such a way locks you into one, and somebody can manipulate and lock it into something else. But if you turn it into a definite integral, you're going to get the same numerical answer. Okay. Questions yet? Anybody with questions? No? Okay. Man, we're just moving right along. Let's see. Third one. Let's evaluate the integral from 0 to 3 of x cubed minus 6x in terms of x dx.
Should you just put this one into your calculator?
Yes, you can. But, yeah, you can do it in your calculator. But remember, on the AP, you may not be able to use your calculator on each part. So if it's easy, chances are you're probably not going to have your calculator. They're going to give you the calculator on the more difficult stuff. So what I would do is I would break this up, 0 to 3 of x cubed. You'll get to a point where you don't even have to break it up in terms of x. Minus, oh, there's a constant, I'll pull that out, x from 0 to 3 up to x. You know, as we're learning, we'll break it up into the pieces. Pretty soon you won't have to do that. Okay, here. I got that power rule again. Barron said add 1 and put it over that same numerical value. And I don't have anything out in front, okay? Plus c technically. Well, no, not plus c. I'm gonna take that from 0 to 3. Actually, let's save all that. We'll do that then, at the very end. Then I got minus 6, x squared over 2. I do have that 6 out here. And then all this, I'm gonna take from 0 to 3. Okay, so what I need to do, I need to plug in 3. My antiderivative has 2 parts. If you want to say that's minus 3x squared, right? So upper bound first, okay? This antiderivative with the upper bound plugged in, 3 to the 4th power over minus, we'll say that's 3. 3 squared. 3 squared. Okay, that's the upper bound plugged in. Minus, let's plug in the lower bound. 0 to the 4th over 4. Minus 3, 0 squared. So I've got 3 to the 4th power. Let's see, that's 9 times 9. 81 over 4. Minus 27. I keep doing the parentheses because with multiple terms, I see it every year. If we release the parenthesis too early, a lot of people will just do minus that first term. And man, it won't matter here because that second term is going to be 0. In fact, the whole thing is 0, right? So I've got minus 0 minus. That's just going to go away. But don't get rid of the parenthesis too early. Okay, if there were several numbers in here, be careful. Okay, so my answer is going to be 81 over 4. We want it 27 over 4.
27 minus 27.
Oh, I don't get the English.
Here, I'll do the bottom. 54 twice 108.
What?
Is this 108 over 4?
Yeah.
54 and 50. So that is negative.
Negative 6.75.
Oh, I don't like this. But yeah, if you're allowed to use a calculator, I guess you could say that.
Or
But,
27. Wouldn't it just be 27?
Yeah. Negative 27. Yeah. Notice that gave me a numerical value. No plus C. We having fun yet? Everybody having fun? Okay. Hey, we're on to number 4 already.
Makes sense.
Look how fast these things can go.
Time flies by when you're having fun.
Number
Right?
the integral from 0 to 2, a definite integral. Why don't we break this up? I'll break it up over here, save some space. Let's see, I can bring the 2 out and do the integral from 0 to 2 of x cubed dx. And I could probably bring the 6 out and do the integral from 0 to 2 of x dx. That'll be easy. And what am I going to do here?
Yeah. Fine, take the antiderivative.
Well, I'm going to have to do the antiderivative. But do you see I could actually pull a 3 out here? The integral from 0 to 2 of 1 over x squared plus 1. Now, why would I do that? I don't know. I remember some formulas on there having 1 over something with squared terms in it. Maybe it matches up with something. I don't know. Anyway, let's see. Here, I've got this 2 outside. Isn't that just going to be x to the 4th over 4?
Yes.
And I got this 6 out here. That's just going to be x squared over 2. Plus 3 times. Now I got to look at the formula sheet. Is there anything that has 1 over x squared
Yes.
plus 1? Which is why I pulled the 3 out, because I see a lot of 1 overs.
Negative tangent. Or tangent.
Inverse tangent.
Inverse tangent.
Inverse tangent.
Plus
Of
x
x.
plus c.
Yes, but we don't need the C here because we're gonna be taking it, the whole thing,
Oh, yeah.
from 0 to 2. That replaces me. Okay, so, hey, I got 3 terms here. Well, let's clean it up first, right? X to the 4th over 2 minus 3x squared plus 3 inverse tangent x. And we're gonna take that from 0 to 2. Okay. But yes, I got 3 terms here. So here's what I'm gonna do. Plug in the upper bound first, 2. So I got 2 to the 4th over 2 minus 3, 2 squared, plus 3 inverse tangent of 2. And I am going to subtract plugging in the lower bound, which again is 0. You're gonna see that a lot if you have to do it by hand. 0 to the 4th over 2 minus 3, 0 squared, plus 3 inverse tangent of 0. Okay, let's see what I get. That's really 2 to the 3rd, 2 times 2 is 4, times 2 is 8, minus 12, plus 3 times inverse tangent of 2. I have no idea what that is. So you know what I'm gonna do? Keep a 3 inverse tangent of 2. Don't know what's okay. Minus what I'm gonna get over here. I'm gonna keep all that in one parenthesis to remind me to keep all of this in. Well, that's gonna be 0 minus 0. Inverse tangent of 0. What angle causes tangent to be 0? 0. Ah, we kind of lucked out here. I got all zeros. Okay, so this is gonna be negative 4 plus 3 inverse tangent of 2. Unless I had a calculator and I could actually figure out what that is. Plus C? No. No. Definite integral. No plus C. Yeah, if you get something that's, you know, I'm gonna need a calculator to figure this out. You could just leave it like that. I would say even if you had a calculator portion of the test, you could leave the answer like this. Because remember, you can leave, if all you have to do is sort of the arithmetic, that's a fine answer. You don't have to figure out what that is. Any questions on that? What? Man, this must be too easy. There's only 2 more to go and we have a whole lunch to do it. That's it. Uh-huh. I love these. Because sometimes we forget. Yes, it looks horrible. But what do I have in the denominator?
You pull out.
Only 1 term.
So you can just split it.
I would split it up. I would. So that's gonna be the integral from 1 to 9 of 2t squared over t squared plus t squared times the square root of t over t squared minus 1 over t squared. All of that in terms of t this time. Of course, if you put it in a calculator, you could just make all the variables x. And then maybe I will simplify this 1 to 9. Hey, the t's squareds are gonna cancel out, right? So that's just 2. And the t squareds are gonna cancel out, so that's x. Maybe you want it to the 1/2, because we don't like radicals. We like exponents better. And, since, why did I call it x? Sorry.
It's t.
T, you're right. And that's gonna be minus t to the minus 2. Okay, if you want to, we don't have to break that up anymore if you think you're ready. That's going to be, let's take the antiderivative. Isn't that gonna be t to the 1 over 1?
Yeah.
So that's gonna be 2t.
2t.
Plus, oh, I've got t, one more. T to the 3/2 over 3/2.
Yeah.
Instead of dividing, let's multiply by the reciprocal. And then minus t to the negative 1, we're adding 1, remember? Not negative 3, over negative 1. And we're gonna do all that from 1 to 9, right? And if you want to, we can clean that one up. That's gonna be 2t plus 2t to the 2/3 over 3, I'm sorry, 3/2. Minus minus plus 1 over t, taken from 1 to 9.
Oh, that's neat.
Okay, so that's gonna be, we got 3 terms, be careful. 2 times 9 plus 2 times the, however you wanna do that. Yeah, 9 to the 3/2, we'll keep it the way it is, over 3, plus 1 over 9. And then we're gonna subtract everything with the 1 in it. So 2 times 1 plus 2, 1 to the 3/2 over 3 plus 1 over 1. So let's see what we got here. We're gonna have 18. What do we got here? Here's what I like to do when I have rational exponent. I could raise 9 to the 3rd power and then take the square root of it. I'd rather make it smaller first. The square root of 9 is 3, and 3 to the 3rd power, 27. Plus 1/9. Yeah, I always like to do the denominator first. Take that root and then raise it to that power. And over here we've got, oh, this is easy. 2 plus 2/3 plus 1. Here, we'll continue over here. It's gonna equal 18. Let's see, I can cancel that 3 with this and have 2 times 9. Well, that's gonna be 18 also. Plus 1/9. Minus what's about to come up over here. 2 plus 2/3 plus 1, that's 3 plus 2/3. 3 plus 3/3. Isn't that just, these two are 3, so isn't that 9/3? Plus 2/3 is 11/3. Because I'm doing this without a calculator. Oh, well. Good, we're gonna have to multiply that out. How can we do that without a calculator? You would have a really good question. Let's see. So, we've got 36 plus 1/9. Minus 11/3. Anybody do 36 times 9 in their head? It's gonna be 36 less than 360. Because times 10 would be 360, so what's 36 less than 360?
No,
324. 324. We got 324. 324 plus 1, 325. Over 9. Minus, let's make this one 9. 3, 33. 9. Of course, if you have a calculator. That's going to be 292. And I always check the signs. There we go. Of course, if you had a calculator. Oh, look, I got the same thing. Yes, but I strongly suggest when you have a rational function, see if you can break it up really easily. If you've got one term in that denominator, man, it's so easy to break up into separate terms. So easy. Is that the only way we could have done it? No, you're gonna find out there's another way, but it's gonna be probably a little bit more complicated than you needed for this problem. Because the other way to do it is great if you have a more complicated problem. Yeah, you could do it. Probably didn't need to. How are we sitting so far? Shall we try the last one? Is everybody having fun? I don't want to have too much fun.
This is physics.
Too much fun is not allowed in high school. Just certain amount. Word problem. Particle moves along a line, so its velocity at times t is velocity. Velocity is a derivative, right? I know that this is actually the derivative of s. We've been calling it s, right? Derivative is the velocity measured in meters per second. Find the displacement of the particle during the time period 1 to 4. What am I gonna need? Displacement. That means it's movement.
Antiderivative of velocity.
Yeah, I'm gonna need this. I'm gonna need that for displacement. Didn't say find the velocity between the two. Okay, I'm gonna need that. So I'm probably gonna have to take the integral of t squared minus t minus 6 dt from 1 to 4. Now, yes, I can split all these apart and do them, you know, like that, like we did. But since I already know that now, can I just do this? That's gonna be t cubed over 3 minus t squared over 2 minus 6t. I'm gonna do all that from 1 to 4. Hey, let me do this. Back it up a little bit. S of t is this. S of t is the antiderivative of this. And there's the antiderivative. So let's see what the value is. Let's see, I want to first take these three terms and plug in 4. So 4 cubed over 3 minus 4 squared over 2 minus 6 times 4. And then I'm going to subtract what comes next, plugging in the 1 for the t. 1 cubed over 3 minus 1 squared over 2 minus 6 times 1. 64 cubed, that's 4 times 4, 16 times 4.
72. No, 74, right?
64. 32 twice.
Yeah.
64 over 3. 8 over 2. And what was that? Minus 24. Minus. No. 1/3 minus 1/2. Minus 6. Yeah, we'll figure it out. 64 over 3 minus 28. Minus, let's see, we can put all that over 6, right? 2 6 minus 3 6 minus 36 6. That over 3. I wonder what 28 times 3 is. 56 plus another 28.
84.
84. 84 over 3. And man, it'd be nice if we could get this down to a 3. Minus 39, 2 minus 39. Of course, negative 37. Over 6. Doesn't look like I'm going to be able to get that down to a 3. So why don't I just make that one 6? 6. Double that, 168. Plus, this is a great example of if you don't have the parenthesis of the whole thing, you're going to subtract that. And then forget to do it here. Plus 37 over 6. Equals
205.
Yeah.
205 over 6. Of course, if you have your calculator, you can. Does that look right?
Yeah.
Does it? So I got something slightly different here. 64. Yeah. Minus 37 is. Plus 37 over 6. Oh, I got something different here.
These are in the first one,
Yeah.
4 squared divided by 2 is not 4.
Oh, yeah.
Where did I do that?
On
The next one.
the very first parentheses.
Or yes, that one? Yeah, that one.
Yeah.
That one doesn't equal 4.
Oh. That'll do it. Thank you. Man, I've made arithmetic errors. So yeah, that's gonna be 16 over 2, right? So that changes, that becomes minus 32. And if I have to put that over 3, that's minus 96 over 3. Hey, check my arithmetic, we already know I'm not doing well. So what is that? Oh, this is a negative. This comes out to be a negative. 32. Is that right? Yeah. Yeah. Negative 32. And we were okay on the second one, right? minus 37, minus a negative 37. So what does that give? Oh, and then we had to, oh, this is minus, we're doubling it, minus 64. Sorry. So 37 minus 64. 27?
Yeah.
Negative 27, right? Negative 27%. Sounds much better. Negative 27%.
You can divide by 3.
Yes, we can. Yeah, we can. Hey, they will not penalize if you didn't give it in a reduced form because it's the same value. Just like, I bet if you had to do this by hand, you could have stopped somewhere up here, technically. Unless you needed that answer for another part of the problem.
Don't you need a unit at the end? Meters?
Oh, yes, we did give the units of measure. So this is going to be distance meters. And what was part B? Find the distance traveled during the time period. Hey, you know what I think? I think it went backwards. So that means my integral was the net. I'm gonna have to add something back.
Negative 64 over 6 is that. But instead of subtracting 37, you're adding 37.
And then what would I get?
9, 10, 101 over 6. Meters traveled.
Where was it turning negative is what I have to figure out. Does anybody know where between 1 and 4 it was turning negative? Because that's the part I have to add back. So where between 1 and 4 did it become negative? At 3.
At 3.
At 3.
Oh, okay.
Because that's not
Yeah.
between 1 and 4. So at 3. Was it after 3 or before 3?
Before.
Because if I plug in 2,
Wait.
if I plug in 2, I get a negative. If I plug in a 4, I get a positive. So I think it's negative here. That's the part I have to add back in.
So you do each from 1 to 3, then 3, 4.
Yeah, so now I can't just change one of these. I have to do the integral from 1 to 3, which I know is gonna be a negative. I'm gonna have to change that one. Well, actually, you know what I can do? Yeah.
Did you just, like, I don't know what it's called in English, but the 2 lines, so it's positive?
Yeah. Absolute value.
Yeah, absolutely.
Yeah. Yeah, we could do that too. We could say, hey, let's just absolute value this thing. I was just gonna make it the opposite sign, cause I knew it was gonna be negative. But yeah, we can absolute value, from 1 to 3 of that equation. But don't we know what, here, let me write it down. Right, and then we already know, well, no, we don't. We're gonna add the part from 3 to 4. So I know this is the part I have to absolute value, or make it the opposite. I know this part's already gonna be positive. Hey, don't I already know what the integral is?
Yeah.
The integral is right here, right?
Yeah.
There's my integral. So I just have to plug that stuff in. I gotta plug it in, here's what I got, I'll just write it down. Over 3 minus t squared over 2. We already figured out the integral, over 2, sorry. Minus 6t. This one, we're gonna need to take from 1 to 3. And you said absolute value it. I got another line. This is where I kinda like to go. Hey, let's just do the opposite sign of whatever I'm about to get. Let's just do the opposite sign. And then I'm gonna add to that this same thing. T cubed over 3 minus t squared over 2 minus 6t taken from 3 to 4. So I need this piece plus that piece, and I need to change the sign of this piece. I already know it's gonna be negative, it's gonna become positive. Since we're close, you want me to just give you the answer?
Yeah.
And the question was the distance traveled. Sorry. So, yes, when you know part of it's negative and they ask for the total, it's probably meaning some of it was negative that I have to add back in. You have to find the part that's gonna be negative. If you get a calculator, you can just graph and see where it's negative. If you don't have a calculator, you're gonna have to figure out where was it negative. What's the part I have to add back in? What's that part I have to absolute value or make the opposite sign so that it gets added back in? Okay.